Go ahead, take a deep breath. Feels like you're breathing in nothing, right? Just air. But what if I told you you've just inhaled a chaotic storm of trillions upon trillions of tiny particles, all zipping around faster than a speeding bullet? Well, that's the world we're diving into. We're going to pull back the curtain on the kinetic theory of gases and see how all that microscopic chaos actually creates the predictable world of pressure and temperature we live in every single day.
But first, let's start with a mystery. Take a look at this. It's a railroad tank car made of solid steel, and somehow it's been crushed like a soda can. No, there wasn't some giant machine involved. The culprit was something totally invisible, something that's all around us right now. And trust me, by the time we're done here, you'll know exactly what did this.
So, to solve our mystery, we have to start small. I mean, really small. Section 1. Gases, a world of atoms. We need to zoom way in and figure out what a gas actually is. And at its heart, it's just a huge, messy collection of atoms or molecules, all in constant, random motion, just filling up whatever space they're.
And when I say a huge collection, the numbers are, well, they're insane. So big that counting them one by one is just completely impossible. Which, gives us a pretty big problem. How on earth can we talk about a specific amount of gas if we can't even count the particles?
Well, scientists came up with a really clever workaround, the mole. Honestly, the easiest way to think about it is like a dozen, but for atoms. You know how a dozen is always 12, whether it's eggs or donuts? Well, a mole is always the same number of particles. And for the record, it's specifically the number of atoms you'd find in 12 grams of carbon-12.
So what is that magic number? It's called Avogadro's number, and it is gigantic. 602 sectillion. That's 602 followed by 21 zeros. This number is absolutely crucial. It's the bridge that connects the tiny, invisible world of individual atoms to the world we can actually see and measure, the world of grams.
Okay, so now we have a way to count these countless particles. Let's move on to Section 2, Life of a Molecule. Now, to understand how all these particles behave, we need to simplify things. Physicists love a good model, and when it comes to gases, their favorite is called the ideal gas model. So, what is an ideal gas? Well, it's not a real gas, but it's an amazing approximation. We just assume a few things. The molecules are basically tiny, hard dots zipping around like microscopic billiard balls. They're so far apart that they pretty much ignore each other. They just fly in perfectly straight lines until they bounce off something. And what's so cool about this is that even though it's a simplification, this model works incredibly well for real gases.
And that beautifully simple model gives us this beautifully simple equation, the ideal gas law. You've probably seen it before. PV equals nRT. This is the golden rule for gases. It connects all the big picture stuff we can actually measure, like pressure, P, volume, V, and temperature, T, with the amount of gas we have, which is N.
So, back to our tank car. It's time to solve the mystery. A crew cleans the inside with hot steam, which is a gas, and then they seal it up. At that moment, the pressure inside is the same as the atmospheric pressure outside. Everything's balanced. But then overnight, two big things happen. First, the car cools down, so the temperature, RT, drops. Second, that hot steam condenses back into liquid water. This means the number of gas molecules, N, drops like a rock. Now look at our law, PV equals nRT. If both T and N on the right side go way down, then the pressure, P, on the left side has to plummet. All of a sudden, that huge, constant atmospheric pressure on the outside isn't balanced anymore, and bam! It just crushes the steel can. Mystery solved.
That tank car is the perfect illustration of what the kinetic theory is all about. Which brings us to Section 3, From Chaos Comes Order. This is where we connect the dots and see how the big, macroscopic things we observe are a direct result of all that invisible, chaotic buzzing on the microscopic level.
Let's start with pressure. We tend to think of it as a steady, constant force, but it's not. It's actually the combined result of trillions of tiny molecules slamming into a surface over and over and over again every single second. It's a molecular hailstorm.
And now for the big one. This is the core idea of the whole thing. What is temperature? It's nothing more than a measurement of the average kinetic energy of the molecules. That's it. Hotter just means the molecules are, on average, moving faster. So when you touch something hot, what you are literally feeling is its molecules jiggling and vibrating like crazy. I'll say it again because it's that important. Temperature is motion.
And how fast are we talking? Well, get this. At room temperature, your average hydrogen molecule is moving at over 1900 meters per second. That's almost 4,300 miles an hour. We're not talking about a lazy drift here. These things are microscopic bullets.
So, let's look at that ideal gas law again. Section 4, a microscopic view. Now, when we see PV equals nRT, it's not just some random equation that happens to work. We can see it for what it truly is, a direct mathematical consequence of the fact that pressure and temperature are just names for what billions of tiny molecules are doing.
But of course, in this chaotic molecular storm, not every particle moves at the exact same speed. You've got a whole range. Some are slow, some are fast, some are in between. So we can talk about the most probable speed, or just the simple average speed, but the one that really tells us about the energy of the gas is called the RMS, or root mean square speed. It's kind of a special average that gives a little extra weight to those super fast molecules, since they're the ones carrying the most kinetic energy.
Now, just when you think you've got it figured out, things get even more interesting. Section 5, storing energy molecularly. It turns out, different molecules can store this kinetic energy in different ways, and it all comes down to their shape.
So take a single atom, like helium. It's just a tiny little ball. It can only move in 3 directions, right? Up and down, left and right, forward and back. We call these degrees of freedom. So a single atom has 3. But now look at an oxygen molecule, which is 2 atoms bonded together. It looks kind of like a tiny dumbbell. So it can move in those 3 directions, plus it can tumble and rotate in 2 different ways. So it has 5 degrees of freedom, 5 different ways to store energy. So what? Why does this matter? Well, imagine you pump some heat into a gas. That energy has to be shared among all those available degrees of freedom. For our helium atom, all that new energy goes into making it move faster, so its temperature goes up pretty quickly. But for the oxygen molecule, that same amount of energy has to be split between moving and rotating. Less energy is left over to make it move faster, so it actually takes more heat to raise its temperature by the same amount.
All right, for our final section, Section 6, Theory in Action. Let's pull all of these ideas together to solve one last, very common real-world puzzle. We know now that these molecules are moving incredibly fast, but, and this is a big but, they don't fly in a straight line for very long. They are constantly crashing into each other. The average distance a molecule gets to travel between these collisions has a name, the mean free path. And in the air you're breathing, that distance is unbelievably short. Which brings us to our final question. If a perfume molecule is flying out of the bottle faster than a bullet, why doesn't the scent hit your nose instantly? Why does it take a minute to waft across the room? Well, the answer is the mean free path. That molecule's journey isn't a straight shot. It's a chaotic, zigzagging, billion collision random walk. It gets bounced around left, right, up, and down by all the air molecules in its way. And there you have it. The kinetic theory doesn't just explain pressure and temperature, it explains the very pace of the world around us.